So feel free to ask me questions. I only really have one purpose in this lecture, and that is we're going to be building microscopes in the lab like this one, and I'm hoping to impart enough information to you all so that you can accomplish that task. We got 2 hours. We can talk about anything else that you want, and maybe some of the slides will inspire things like that. But you'll notice the error on the first slide is I didn't cross off the names of the people who weren't actually involved with this. So this is Dr. Stephen Nagel, and we're both Stephen. It's real easy, and we're going to be on top of you guys in the lab. So we'll be. You get a lot of help doing this thing. I hope. Definitely one of those days. Okay. So, as I just said, you're going to build a microscope, and then we're going to use it to measure some stuff and look at cell differentiation. And usually when we teach our instrumentation class, it's a required class, so I feel like I have to spend a lot of time explaining why anyone would do such a thing. And since you're all here voluntarily, I'm going to skip all that in favor of the limited time we have. But if you do have any questions about, why you would do this thing and why it's important to understand what's inside of the instruments and how that helps you use them to your maximum advantage, get an unfair advantage over the many other researchers looking at the same problems you are, I'll be happy to spend as much time as you want on that. This is one of my favorite quotes, the Yogi Berra version. I've traced it back through history. I was quite happy to see how far back I could find a version of the quote from Hevelius in 1611. But basically, that's why we do this in the lab. I talked about the goals, what I'm going for in this lecture. And then just in sort of way of outline, we'll just talk about what's inside the microscope, and most importantly, what limits its performance. And if we have any time at all, what really clever approaches people take to getting around those limits. So after this, we're going to go over, and some of you are going to go to the wet lab, which I think you've heard about, and some of you are going to come over and visit the Instrumentation Teaching Lab. And this is a really cool place. We have more than 15,000 components, and we have about a dozen lab stations. And what we do is, you can see all the boxes of components on the bottom, and we just keep assembling those guys into different stuff. And then mostly I make people take it apart again, and we make it into something else. So it's a little bit, like the monks who make the sand sculptures or something like that. But so we have a really good facility. I hope you enjoy it. But we also have a bunch of other things in there, and CCD cameras and all the kinds of things you'll need. But we can talk more about that. So let me just launch in, and I'm just going to start with a review of the physics of light. And so there have been several important models of the behavior of light in history. And of course, all of these need to be able to explain, the kinds of phenomena you see in the lab when you go in the lab and play with light. And so sort of one of the most basic things along those lines, of course, is reflection and refraction. So I think probably everybody has a pretty good feel for reflection. Light shines on something, goes away at the same angle. And then refraction, materials, when light enters the material, that's, not a vacuum. The material has this property called the index of refraction. And the index of refraction is a measure of how much the light slows down. So the light actually goes slower when it gets inside of something. And I have some typical indices of refraction here. I always thought vodka would be lower than water. But then, you can use this number, and essentially this is, an equation that describes how the light bends, okay? And you can actually, if you want to derive this, you can derive the angle by figuring out, how much the light has slowed down before that. So probably the biggest debate when people were trying to develop any kind of theory to predict the behavior of light was, is it a particle or a wave? And usually I do this as a demonstration. I didn't think we have time today. If anyone wants to see this, we can set it up in the lab. But basically, one of the most important, and this was a huge battle between Huygens and Isaac Newton. And basically, Newton was very hard a person to argue with. And so he had the opinion that light was a particle. And that opinion prevailed for about 100 years. And a very important experiment that helped establish that light was a wave was this existence of this thing called the Poisson spot. And so if light is a particle, and you shine a beam of light on like a ball bearing on a ball, if it's a wave, you would expect there to be a bright spot in the middle. And if it's a particle, it's very hard to explain how that bright spot ends up being there. And so, of course, it was Arago who did this experiment, and he did it. And so this is the experimental setup I usually demo in the class. And everybody knows there was a bright spot there, right? OK. So now we have another sort of aspect that our theory of light has to explain, and that is this wave behavior. So we have reflection, refraction, and diffraction and interference that our theory of light has to explain. OK? And does everybody get why there's the bright spot there? Maybe. All right. Feel free to ask me questions. OK. And then, of course, you know, this I don't know if we're going to actually, it's dim enough in here to see it, but actually you can see that. So this is a laser, and one of the reasons why I use this laser for lecture today and to demo with is this is basically the same thing you're going to use as an illumination source in your microscope. We have little ones that plug into the wall like this, but this is basically it. And we'll talk about how to use this reasonably safely. But basically here I'm putting a slit on there, and you can see, and it's I guess you can see. Yeah, can you guys see that? So it makes this so this is the experimental setup there, and when I put it through, you end up with this pattern of minima and maxima, and you sort of can develop this principle about how you decide what the bright and dark spots are going to look like. You can consider a wave of light, each point on it as a new point source, each point on the wavefront. Okay, and then so when one of the points gets interrupted, you know, by a hit by striking an aperture or something like that, you can kind of figure out what the end result is going to look like. And so this all of this got put together into this classical electromagnetic theory, where light ends up being this wave with electric and magnetic fields transverse to the direction of propagation. And one thing that we're going to do a lot is we're going to draw rays. Okay, and just so it's absolutely clear what these rays are, these rays point in the direction of propagation. Okay, so we're going to do lots of rays today. And so I'm assuming everybody has seen Maxwell's equations before. But then, so it's pretty well. So at this point, it's pretty well settled, right? Light's a wave. We have an equation of it. But then something else, another behavior was noticed. Something went wrong with that theory, and there was a few inklings that different ways that it became clear that the theory would have to be updated. And this is one is basically the photoelectric effect. When you shine light on a metal, the energy of the electrons that come out depends on the color of the light, not on the brightness. Okay, and this was an effect that the electromagnetic theory couldn't explain, right? Because a brighter light is just a bigger electric field, should make the electrons go faster. And so this ended up causing lots of problems. And so the quantum theory answers that sort of nuance of the behavior of light, where you have light coming in these discrete little packets with an energy of hc over the wavelength. So this is my cursory review of all the models of light. Okay, and we're going to use all three of these today. So And it's kind of interesting. They end up being really complementary. If you look at the first subject we're going to talk about, ray tracing, we're basically going to treat light completely as a particle. We're just going to ignore any of this wave-like behavior of it. And that's, a pretty gross approximation, but it ends up that if you want to appreciate the function of a system of lenses, any kind of optical system, the rays give you a really good intuitive way to do that, right? They're the simplest model. To understand sort of the overall functionality of a system, you don't need to model the light in all that much detail. So then we're going to move on. We're going to start talking about resolution. And in order to understand resolution, we'll have to bump up the level of detail a notch and start looking at the wave theory, okay, and looking at diffraction. And then when you start talking about noise in images and also fluorescence microscopy, you have to be very careful about how you model the behavior, and that relies on the quantum theory. All right, enough introduction. Everybody happy so far? Okay, so let's do some problems. Okay, so right now we're just right in this classical in the particle theory. Okay. All right, so I have this sort of contrived situation. Actually, ends up being pretty useful. So I have air here, piece of glass here, say, and I have a spherical surface on the front of this, and I have some kind of a luminous object. Okay, and what we want to do is we want to get a handle on what's going to happen to the light as it hits that surface. Okay, and so I started out. So my example object here is a lamp. It has a filament, and I can draw. So the light that comes from here goes off in all directions. So I can draw, rays, representative rays, in any direction I feel like, right? And so I've drawn just one example here, and that strikes the surface here with an angle θ1 to the normal, and that's going to be refracted. And of course, I can go and I can solve this exactly using Snell's law, which I showed, a few slides earlier. But there's a little. You always make this, whenever you solve any problem, you always make the same approximations. And one of the great approximations in history is the small angle approximation. And so, of course, for that they call it the paraxial approximation. I'm basically just going to assume that the angles are small, so θ equals sine θ equals tangent θ. I'm going to make one more assumption. I'm going to assume that the lens is thin. All right, so I'm just like wishing away all the parts of this problem that are difficult to solve, okay? And then maybe in a little bit we'll talk about what happens when you start violating the assumptions, all right? So I'm wishing away the thickness. So this has thickness. I'm just going to wish that away. So I have a thin lens at small angles, and now I can start making some simplifications to these equations, okay? So I can. This is supposed to be a minus, by the way, for those of you paying attention. That was on that way for that slide for 5 years before somebody noticed that was supposed to be a minus, by the way. So here's my law of refraction. I'm going to substitute in for my signs using my paraxial assumption, crunch it, do the algebra and solve it, and I'm going to end up with this equation here, which is called the lensmaker's formula. Okay, and what you'll notice from this is that this distance here, SI, so my object is at a distance SO, and this distance here, SI, doesn't depend on the angle. Okay, and so any ray that I choose to draw coming from that same point is going to cross through this same point again. All right. So everybody's with me, right? I made the same assumptions I always make to solve any problem with the sign in it, and now I get that all the light leaving from one point here crosses at another point there. All right. Everybody's happy. And we can revisit this a little bit. I was a little bit not careful there because it actually depends. So I drew the rays crossing. If I bring my source closer, I can actually bring it close enough so that the rays don't bend enough to ever come together again. Okay, and so this is the situation where I'm less than this magic distance. Okay, and then there's this place where I can put the light and where it's going to come out exactly parallel. Okay, so now we're ready to make a lens. I forgot to bring a lens. We'll see lots of lenses in the lab. Everybody's seen a lens. So a lens is two of these. Okay, and again, just keeping all of my assumptions I did. I can pull this trick that you can always pull in optical systems that's very useful, is you can use the image from the first refraction as the object for the second one. Okay, so this second surface has no idea, you know, where the object was. It only knows what angles the light is hitting it at, right? And so in fact, I can take and just taking two of these surfaces. I apologize. I called that previous thing the lens maker's formula. This is really the lens maker's formula. And then I can come up with this equation, and I get this value f, which is the focal length of a lens. One of the most important things I could specify about a lens, right? And you'll notice that there's a weird sign convention on the second radius in this. And if you ever have to grind a lens and want to get the radius right, make sure you get the sign right, okay? All right, so nobody's going to grind a lens here. And but now we have our model of lenses under that set of assumptions. And now we can start talking about how an image gets made with the lens. And so I'm going to put a luminous object here, okay? And we're talking about luminous objects because they're easier than ones that you shine light through. We'll talk about that in a minute, okay? And so I'm just going to take two representative points from this object, and I'm going to assume that, you know, this object is just made up of kind of an infinity of these little luminous points. And I'm just going to consider two example ones, right? And so there are some, I did these in the wrong order, didn't I? Hang on, I'm going to skip ahead to, just going to skip ahead momentarily to slide 23, okay? And so if I really want to boil down the function of a lens using under the set of assumptions I have, I can really turn it into kind of three rules, all right? So the first rule is that the ray that goes through the middle of a lens doesn't change directions, okay? The second rule is that rays that come in parallel to the optical axis always go through the focal point, okay? And my third rule is that rays that are parallel all cross through the same point in the focal plane. And I can, of course, always find this point by drawing the ray that goes through the middle of the lens, okay? And since physicists haven't really figured out what time is, all the rules work backwards, okay? So now you know how to take light that's striking any lens and tell what direction it's going to be going after it emerges. So back to where we were.
Question?
Yeah.
So back to the equation that you just showed us. Is that
this one?
Yeah.
Yeah.
So is that only correct when the thickness of the lens is
That's right.
decimal?
That's right. So there's a version of the equation that takes account of the thickness of the lens. So, but most of the time, right now I'm just going for like understanding the you're going to look at a block diagram of a microscope soon, and I want to be able to explain the functionality of that system. And if the lenses are a little thick, it's not going to make very much difference for right now. But yeah, that's correct. It is not right for thick lenses. In fact, when I draw lenses, I usually draw them as infinitely thin, right? Just because I've assumed that. And when I give the exams, at least to the undergrads, you can pretty much tell that a student's going to get the question wrong if they draw a big old lens there and make the lines bend at the interfaces. OK, so we have our luminous object. All right, there's the first ray I'm going to draw. What happens to this one from our ray tracing rules? Where does this one go? Anyone? That's right. It's going to go right through the focal point. Exactly right. And now I'm going to draw another ray. Okay, this one I also know where it goes, right? Because again, there's no time in any of these equations. So this one's going to come out straight. And now I also can draw the one through the middle that doesn't move. But we know that all of those, I can draw any ray I want now, right? I know absolutely where any ray is going to go. Okay. And likewise, so I can put a screen up here to see my image. And likewise, I can do the same kind of thing and draw any ray I want coming from the white point, right? So the yellow point on the object becomes the yellow point on the screen. The white point on the object becomes the white point on the screen. And then the screen, actually, what it ends up doing is it ends up scattering the light in all kinds of directions. And this is why an image projected on a screen is kind of a convincing illusion, right? Because there's light coming out all directions from this point, just as it would have, had the object been there. And just to be totally clear about what you're seeing when you look at this kind of real image on a screen, that light is getting refracted by your cornea and turned into another real image on your retina. The image is upside down. Your brain turns it right. You interpret that as right side up. I don't know what right side up means, I guess. And so this is just to be crystal clear about. That's what you're looking at. I'm going to not spend very long on this because this is there. Of course, you can make a lens that's curved the other way, and instead of making the light rays bend in, it makes the light rays bend out. Okay, and it follows the exact same formula, except the focus is on the other side, right? And so you use the exact same ray tracing rules, except where a ray coming in would have gone through the focus, now a ray coming in parallel appears to be coming from the focus, right? On the same side that it came from. So we normally use a negative lens in our microscope designs. We're actually not going to be, well, you can if you want. We got lots of lenses. You're welcome to use them. But I think we probably won't be using them much. So you've got 6 possibilities, and we'll talk about why you would choose some of these possibilities in a little bit. We already did this. OK, so let's do an optical system. All right, we have all the information. Before I do, any last questions, ray tracing? So we have all the information we need to solve an optical system now. And I call this thing a beam expander, so you probably have a pretty good guess about what it does. So when you see the question like this, you start drawing rays that are easy to draw and see what intuition they give you. So the easiest ray to draw is this one, right? I generally award one point for that ray. OK, so what happens to this ray? Again, goes to the focal point. And then what I've done here is I've arranged these 2 lenses so their focal points are in the same place. Even though they're different focal lengths, I put them at their sum of the focal distance apart. And now you can see what's going to happen here is the rays that coming in get spread out further apart. And if you just look at 2 similar triangles here, you'll see that I've expanded my beam by the ratio of the focal lengths. Okay, so if I have a little beam like this, I can put 2 lenses in front of it, make it big, or I can shine through the other way. I can make it smaller too, right? Yeah. And this is another application. That we can do just simple ray tracing. So these are the earliest microscopes. forgot to show the video. We'll do that in a minute. These were the earliest microscopes, and so this is so. Do we have anybody Dutch here? So I'm told that nobody who's not Dutch can say this name correctly, so I'm not going to try. So this gentleman was a microscope maker in the 1600s, and he made his microscopes with one lens, and he put that lens very close to the object, and so we can do our ray tracing again with this, and I'm not gonna bore you, but you all seem pretty bored with ray tracing, so I'm just gonna go through it fast. All right. So my first ray goes to the center. My second ray is a little more complicated. We're closer than the focus now. It's the ray that would have come from the direction of the focus. So now I know that one's going to come out straight. And now I'm pretty well done with my problem. What I have is there's no physical place where the lines cross. So there's not a real image. There's a virtual image. There's a place where all the lines seem to be coming from, okay? And I actually can observe that image, again, using the optics of my eye to focus it down on my retina. And that image is farther away and bigger than the original thing. So these were some of the earliest microscopes. This is the same thing as like you would call a magnifying lens. And you basically get the idea why old people like magnifying lenses, because it makes things big and far away, right? And so, but the key point is there's no place you could put a screen and make an image from that directly. This guy was really interesting. He had some of the very earliest reports of observing bacteria just with this little microscope, and he was actually getting powers of like 200x, which was higher than what people using the fancier microscopes could get. One of his places he liked to look at bacteria was in the plaque of people's teeth, by the way. So anyway, so he this is for that single lens microscope. This gives you an idea of the image versus object distance. And of course, if you look at this diagram, you can see that you're magnified by the ratio of the distances, right, for this guy. So this was a cool microscope, and what we can do is we can, just to get, oops. So there's many simulators of this on the web, but so this is one example. So remember, he put his object closer than the focal point, and if I click virtual image here, so there you can see that first of all, I have to put this thing very close, and I can make the image quite big. And there's certainly still people who advocate for this this design, but there's some real problems getting that to work. Like, it's pretty inconvenient to hold that thing up to your eye for a long time. Let's see, how do I get this back? There we go. All right, so there's lots of those simulators on the web. So now this design now, what I'm showing here, this is what most modern microscopes are, okay? So you have two lenses. You put the object, I don't want to go into too much detail, but this is how the modern design works. And basically, if we draw some rays here, we end up with the object getting magnified by the ratio of their focal lengths of the lenses. All right, nobody wants me to do that faster, right? Or slower, right? Okay, good. And of course, it's inverted. You get an inverted real image at the end there. So let's do one of these, okay? So we can make an example of one of these, and I have this here, right? I have a microscope objective and a lens. But before we do that, let's talk just a little tiny bit about microscope objectives. So inside of here, there might be 3 or 5 or 7 or who knows how many lenses. And so this is actually a pretty complicated optical system in itself. But again, in terms of this, just like viewing the gross functionality, we can model this thing as a single, simple lens. Okay? And by way of analogy, this lens has this thing printed on it called the working distance. And that working distance, if you go 0.65 millimeters from the frontmost optic of this lens, that place is an analogy for this focus. Okay? And so this lens, of course, has a front focus and a back focus. And this back focus is not, it depends on the magnification of the lens. It might range from way up inside the tube of the lens to actually outside. So high-powered lenses, this point is up close, and low-powered lenses, it tends to come outside of the objective body itself. And so there's a bunch of other stuff printed on the objective. And one of the other things that's important is this tube length. So there's almost always a little infinity symbol there for modern microscope objectives. And there used to be a number there, like 200 or 170 or something. And that number used to be the distance to the imaging plane. So nowadays, most microscopes are designed so you put the sample right in the focal plane, and you need another lens, to actually form an image. And of course, the magnification, NA we'll talk about in a minute. But since this tube length number is not there anymore, there's still a sort of a phantom of it. You kind of have to know what it was, what it used to be. And they don't print. It's an important number, and they don't print it anywhere, of course, on there. And so for Nikon, and it varies by manufacturer. So for Nikon, this is called the reference tube length. It's 200 millimeters. So if you want to know the focal length of this sort of lens, single lens model of this guy, you take 200 and you divide it by the magnification number printed on the side of the objective, right? So this is the equivalent of a 5 millimeter lens. The interesting thing is if you screw this lens into a Carl Zeiss microscope, which has a different reference tube length, you don't get 40x. You actually end up getting 50x, right? Because it's a different tube length. Very, very confusing thing. And then I'm just going to make one practical note. These guys have a different thread than most of our optical components, so you got to use a thread adapter to put them in, and we'll show you all that stuff. Yeah? Everybody happy with the, yeah?
So I just want to know, like, what does it mean exactly when it's 40x? Like, what is the definition?
So you're right. So it's very funny. It's the biggest number they print on the objective, but it's the most useless number. So basically what it means is the focal length is 200 divided by that number. It really doesn't mean anything else. Because the actual magnification you get assumes it's in some kind of an optical system. And so Nikon is assuming you're going to screw it into one of their own microscopes that has a 200 millimeter lens there. And that's where the 200 comes from. Right? So it's kind of a, but that's what it means. So on a Nikon objective, it means the focal length is 200 over 40. On a Carl Zeiss objective, it means it's 170 over 40, right? Is that, you look a little, we can talk about it more. It's the biggest number and the least valuable number, is my opinion. Incidentally, does anybody have a pick for which number, if they could only have one number, which one would you pick to know? Yeah. So this is the NA. That's really we'll talk about why it's important in a minute. Okay. All right, everybody. Any more questions? All right. So here's my demo. Okay. Oop, I forgot to run the software before we came. So this is the setup I have here. I have an illuminator. This is a little LED flashlight. And then I have a sample here, okay, and this is called an Air Force target. It's some thing that people have been using for I don't know how many years to look at imaging systems. But one thing that's useful about the Air Force target is that it has these markings on it that are a known width apart. So I'm hoping Okay. So, and one of the reasons why I'm showing this demo is it's made out of all the same stuff that you're going to be using to build a microscope out of, okay? So I have a CCD camera here, okay? I have a 200 millimeter lens 200 millimeters away from there. And then I have my microscope objective 200 millimeters away from that lens. So this is, they call this the infinity space. This is where the I have my tube lens, and now it's converging to form an image, okay? And so I can adjust this around a little bit. So you can see that's a 16. Where'd my 18 go? $14, 16. So this number here is telling me, oh, there, is that it?
Yeah, you have to adjust the post.
No. Oops, wrong thing. So this number tells me how many line pairs, so a line pair is a black and a white, per millimeter there are. Okay, so here we are. So this is 18, okay? And so I'm sorry that you can't see this, but I have my camera controls over here. And I'm going to adjust my exposure to be something more reasonable. And then I'm going to focus this thing up. So I'm changing the distance of the sample. And so I can use this to measure my magnification, right? Because I know how big the lines are. Need one more piece of information. And that is on here. So I have the camera is an array of 640 by 480 pixels. You can think of it as a piece of graph paper. I shine a certain amount of light on each square, and that's how much I see on the screen. And there's 7.4 micron square pixels on the graph paper. So I'm going to save a little time, I pre-computed the magnification. So what I did is I used this image that I took from the camera, and I counted the number of pixels in 4 lines, and I did it carefully, and I got 302. And then, so if you go in and we do this calculation, so I have 300, oops, you have to be able to see that, right? Not just me, okay. So if you do this calculation, I had 302 pixels times 7.4 microns. That's how big my image was, right? And then I had 4 lines and 18 lines per millimeter, right? And so if I hit go on that, I get a magnification of 10.0. Dr. Nagel built the setup, so it's dead on, of course. And so that objective says 10x on the side of it. Okay, so everybody understands why I got 10. And that this is a focal length. This is a 20 millimeter lens, right? Okay. So we'll go back to the presentation here. All right. So now, so by the way, doing this magnification check when you build your scope, as soon as you have it working, do that, because that'll point out if you have some value wrong, right? You know. And so I'm going to use this as an opportunity to show you a little movie. So I keep talking about building a microscope, and I meant to show you this right at the very beginning of our discussion. So this is the lab you're going to be doing, a little bit condensed. Let's see, how do I make this full screen? I don't know how to make it full screen. So there's kind of I forgot the music that goes with it. I'm apologizing. So there's kind of a part where they're sort of building now a support structure, and of course you have to think about how you're going to build a support structure, because it needs to hold things in very precise places. Some things matter, some things to sub-millimeter accuracy, other things not so accurate. And then there's this big post in the middle. That's kind of a central pillar that everything gets anchored to. So that's a nice stable spot. So hopefully things don't wiggle around too much. And then there's this box here. We'll talk about that in a little bit. That's going to hold our optical filters for doing fluorescence, some of them, okay? And this box has this little round cap on it, and that round cap lets you adjust the optical, how the filters point. And then, so pretty soon here, so they're going to be putting a camera on here in a minute. All right, so that's the CCD camera. The imaging lens, the tube lens is here. This is a distance of 200 millimeters. And so, yeah. Should I tell them the secret of that video or not? No, we'll keep it secret. All right. So anyway, that's what you're gonna do in the lab. And then, of course, we're gonna put all the interesting samples you're making in the wet lab on it and look at them. All right. And does that sound good to everybody? Are you guys excited about that, or is this all right? All right.
You must give us good coffee.
Yeah, more coffee, yes. All right. So I'm gonna. I don't think we're gonna have time for everything. I'm gonna skip over this a little bit, but it ends up that your illumination is also really critical to achieving resolution. If we have time, maybe I'll come back to this. But basically, the way it works out when you set up an illuminator, you might have like a light bulb or some crazy thing that's not very uniform. And by setting up the lens system right, you basically end up looking at our ray tracing rules. If you put this a focal distance away, each point on the illuminator ends up becoming an angle in that shines through the sample. And that helps make it more uniform. But also, in order to get the best picture we'll talk about in a minute, you need a lot of angles of light. Except for some imaging modes, you need very few angles. So it depends on what you're doing. All right. And has everybody adjusted a microscope for color illumination? Who has adjusted? Who knows how to do color? Okay. So we have a sort of an old clunker Nikon microscope in the lab. I'll show you how to do this and I'll explain it while I'm doing it better. But basically, there's kind of a way that you adjust the scope so that you make the conditions true that I just said, that the light is very uniform and that you get your best resolution and contrast. And I'll draw it out carefully while I'm we'll do it in small groups maybe in the lab. Somebody asked me to explain phase contrast, which I'm going to do if we have time at the end. And then there two other important properties. So we've been kind of thinking about these ideal infinite lenses, and of course, an obvious limitation. We had a question already about the thickness of the lenses, which makes them different and not as ideal. But also, they have a finite size too, right? And so when you're considering how the size of the optics affects your system, there's these two pretty useful concepts of the aperture stop and the field stop. And so the aperture stop is whichever physical element. It might be a lens that's of a finite size, or it might actually be an iris or whatever. It's the element in your optical system that limits how much light the thing can gather. So for example, in this system here, you can see that some rays that would have gone into the optical system are falling on this stop, and so that's the thing that's limiting it. So this is the thing that limits the angle of the on-axis light that comes in. And of course, the other thing that happens is you can't see everything. You have a limit of your field of view, and so there's also an element in your optical system. It might be the same as the aperture stop. Frequently, it's not. In a microscope, you design it to be purposefully different, this is the thing that limits how much of a sample. What's your field of view? How much you could see. And this basically is the element that limits the angle of the off-axis light that comes into the system. Okay. And again, I'm not going to go. There's a sort of like a recipe for finding out which one is which, and we're not going to have to worry about too much. This is Robert Hooke. So as far as I know, there's no surviving images of Hooke that were contemporary. This is a modern painting. So if you Google him, there's a couple on the web that claim to be Hooke, but then if you look into it a little deeper, they're disputed. And so nobody is totally sure what Hooke looked like, except it's kind of universally agreed that he was not a particularly attractive man. He was a very early adopter and advocate of the compound microscope design. And of course, although van Leeuwenhoek saw bacteria and stuff, he was the first person to really record and report and measure cells. And he, in fact, named them cells, right? And as far as I can tell, this is one of the earliest quantitative measurements of cells. It's the earliest one I can find. There might be something else, but he didn't just see them. He counted how many there were in an 1/18 of an inch for some reason. I don't know why that was. But anyway, so this was his microscope. But one thing, and a lot of people were looking at biology with microscopes then. But the thing about Hooke is he could draw, and he could draw like nobody's business. So he trained as a painter, and so this was amazing. This was this is an original copy of his book Micrographia that reported a lot of his doings with the microscope. And I was in San Francisco Airport, and this thing was just on display there. And so I was quite amazed. So if you're flying through San Francisco, it's in the international terminal. Take a look. And this thing, that drawing, I mean, it's maybe a little bigger than actual size. It's unbelievably detailed. And so Hooke had his microscope, and I guess my question would be: he could draw, he had a good microscope. He discovered cells, but he didn't discover DNA or organelles of cells or anything like that. And so, what do you think kept him from doing that? What was Hooke's problem? What was his? Say again? Yeah, that's right. It's violating these assumptions. Basically, his microscope was a piece of crap. Okay, and you probably, if you had to look through it now, you would not. I seriously, you would not be able to believe how he made this drawing using that piece of junk. So we had these assumptions that we talked about at the beginning. And as we move away from these ideal assumptions, things start to go haywire. One of the most important, so optical aberrations were very bad in his microscope. And so when these lines, so this is a demonstration of spherical aberration. So when these lines are close to the axis, like we assumed, they hit pretty much in one point. But if you follow these rays that are near the edges, they cross pretty far away. And again, it's because we're getting away from that paraxial assumption, okay? And the same thing happens when you shine rays at an angle. The extreme rays focus at a slightly different point than the ones that go near the middle, right? And so that creates this artifact called coma. And probably you've seen all of these things in some images from, especially there's a lot of cheap cameras in the world now. This one is an interesting one. So chromatic aberration is that every wavelength of light experiences a slightly different index of refraction in the medium. So this is the medium, the glass is dispersive, okay? And so the red light doesn't focus in the same spot as the green light, okay? And that's extremely annoying when you're trying to make a good image. And another thing that happens is that a plane in the object plane gets focused to be a curve in the image plane, right? So that everything that was that you would think should be in focus that was in a flat plane ends up not being so. And all of these basically arise, assuming that you can actually manufacture a lens to some quality, and grind it to the right shape that you want it. All these arise because we're violating those assumptions. But there are ways to minimize them. So this one is going to be important for building your microscopes. When you, in the lab, so we talked about how there are these, 6 kind of possible lenses, and you want to use them all in the right situation. So when you have, so this is called an infinite conjugate application. So when your light source is far away or the rays are almost parallel, you want to use a lens that's curved on one side, and you're focusing that to a point that's near. You want to use a lens that's curved on one side and flat on the other, okay? And in fact, if you could design this lens yourself and choose any curves you wanted, you could design it for the exact distances you want. But when you're sort of close to this application of focusing parallel rays down to a point, and you actually want to have the curved side facing the straight light, okay? And the way that I remember this is not really a profound, well, I don't know, maybe, but is that if you had the straight light coming in this side, it would hit a flat surface, and that surface would be doing nothing for you, right? It would be doing zero work. And so if you kind of divide the work between both surfaces, that all the angles are a little bit less, all of the assumptions are a little bit less violated, right? And so when you have this situation, such as you're making a laser beam expander, you always want to put the curved side of the lens towards the straight light, okay? And it's the same with the negative lens, curved side towards straight light. If you have a situation where the image our distances are comparable, use a lens that has curves on both sides of it, okay? And you'll get less spherical aberration that way. All right? So there are, and actually another way you can effectively make a very short focal length lens is by combining one of these lenses with one of the simple lenses, okay? And that's why they use these lenses in eyeglasses, because they make there be less, the resulting system of your cornea and lens and your eyeglasses has less spherical aberration, okay? And there's other solutions to this problem. You can make a lens that's not spherical. So this is expensive. It requires a lot more machine time to make a lens this way. Although I think, in some number of years with it's the cost for asphere lenses is going down all the time. And in some number of years, people are not going to, it won't be that significant a difference anymore. We're going to actually use some asphere lenses in this lab that are in the kind of $15 range, which is pretty amazing. And then, so this is chromatic aberration. And so this is, again, that problem where the red, green, and blue focus to different points. Everybody who wears glasses has seen this. This was Isaac Newton's solution to chromatic aberration. He used mirrors instead of lenses because they don't have chromatic aberration. It was a good solution. Here's another solution. You can use more than one lens. So you can basically cement two lenses together, and the lenses are made out of different kinds of glass. So here's the characteristics of some different glasses, and they have different dispersions, okay? And if I design the curve of this surface right, again, this negative surface is going to reduce the amount of refraction the lens makes, but so I'm going to pay for it. But the thing I'm getting is I'm getting the light to come together in a point. But I can only design this to make two colors of light come together in that point. So maybe I'll make red and blue come together. Green will be a little bit off, but it's much better than it was before, right? And then I can do three lenses. And these normally use crown and flint glass. This usually adds this fluorite glass, which you can see is very low dispersion. And now I get two more surfaces I get to play with. And so now I can actually, I guess I only get one more surface since they all have to match. Now I can make three colors of light come together at exactly one point. And so over kind of the visible range, this lens is very, very low chromatic aberration, right? Almost none. And so that's a good solution. Two more clever solutions are your eyes have chromatic aberration like crazy. It doesn't bother you because your brain is used to it. And you can correct it in software sometimes also, which a lot of starting to see in some really cheap cameras and things like that. These are two clever solutions to field curvature. Is you can curve the detector, which has been the design strategy employed by most eyeballs. And also, I forget what telescope this is. Some big telescope. I should, yeah, all right. And then I think that's a space telescope. Okay, so when I'm on vacation, I go around and visit microscopes. And so these are a few that I visited. But you can basically, so this is a Van Leeuwenhoek, however you say it, microscope. This is similar to Hooke's microscope. I haven't seen his. It's actually in New York. I need to go see it someday. But as you go down the years, basically those aberrations get corrected. Okay, this microscope has correction for chromatic aberration. This is early. This wasn't common in 1835, but this is when you're starting to see it. And then by the time you get to 1940, I mean, things are better now, but this has, most of the kind of modern corrections you'd see in a microscope. So I was going to have another picture here. I forgot to change this picture. So you notice there's a blank spot here, and a lot of times, probably on most of the objectives you use, there's words there. And there's a very arcane system of words and acronyms that they'll print there. So these words like acro, fluor, apo, I like Wasser, plano, all these things. And so these will tell you the optical properties of the objective, okay? And so now you should have a pretty good guess at what acro and apo are. So that's the degree of color correction, correction for chromatic aberration. And this plano, that's the correction for the field curvature distortion. And but the thing is with the objectives is now all the microscope companies, they're really competitive and really marketing driven. And so I don't really understand the differences between the objective lines that well anymore. If you just look at the catalog, it's very hard to tell what's going on. You really got to ask a lot of questions. But and there's a lot of other things to consider in objectives. Like some objectives, there are very autofluorescent, and so they might give you a lot of trouble doing fluorescence. But and then of course they don't print anywhere that spec or anything like that. Or there's no word for a lot of the useful things the things that would be useful to know. But anyway, the key thing about this slide is that the manufacturer charges by the word. Okay, so. If you really, the best chart I think is on Nikon's site, and they list most everybody's crazy scheme of words for there. And so, okay, so now we have a modern microscope. This one is actually Barbara McClintock's microscope, and of course she was able to discover transposons before the structure of DNA was known, using just a light microscope. It's about the cleverest thing I can imagine doing with just sort of a plain old vanilla light microscope. And so she still wasn't able, she didn't get the structure of DNA or anything like that, so there was still something preventing from going further. And of course this is a more, and even, you can't even see it on the modern scopes. So there's something kind of more fundamental that prevents you from, that really puts this limit on how small you can see. And so now we're going to start talking in the next, now we'll be in the wave theory, okay? And so I like this dictionary definition of diffraction. It's pretty good. It just basically light changes as it propagates, especially around stuff, okay? And so we already looked at the single slit diffraction. So, and this is another demo I usually do, but I don't think we have time for. So if you shine this laser, I shined it through a single slit and we got that pattern. If you were to shine this through a little pinhole, you would get a pattern that looks like this, okay? And this thing is called an airy disk, and it's described by this Bessel function. And the basic properties of it is it's bright in the middle. There's kind of a bright middle blob. There's a zero. And then there's these kind of bouncy fringes around it. And everybody who's looked through a microscope has probably seen something close to one of these. And so you could do a whole lot of math figuring out this airy disk. But there's kind of a few key things. One key thing is where this first zero occurs, okay? And so you don't need to figure that out. Somebody already did. And I guess this depends on the wavelength. It depends on the wavelength of light and how far you're away, because the thing is getting bigger, right? And so, oh no, I'm sorry, I was wrong. D is the, yeah, this is the size of it, yeah, right. So, whoops, wrong way. So let's rethink imaging again. So now we did imaging with the particle model, with the ray tracing model. Now let's do it again with the wave model, okay? And so in this wave model, we're going to take a source. And by the way, you don't need a lens to image, right? You can just make a hole in a piece of cardboard. And so the light from here, again, in our ray tracing model, would end up as a point there. But in our model with wave behavior, it ends up being a blob, right? It's one of these airy disks, okay? And then, so if I consider my luminous object again, each point on this object is no longer a point in the image. Each point on the object is a blob in the image space. And so this is actually ends up being what limits the smallest thing I can see. And I can consider a lens if I just take my ideal infinite lens and I put some kind of aperture after it, okay? And then I get my airy disk after. And so this is what that turning. So what I've done is mathematically I've taken every point of this image and turned it into a blob, and then added them all together. Okay, and that's of course the mathematical operation of convolution. Okay, so I convolve this image with an airy spot, and you can see how I can almost read the screen. This is Ed Boyden, by the way. When I told him that you could almost read the screen, he was kind of upset because this is his to-do list for the next 30 years. So anyway, you can see how you can't really see that anymore. I guess a little light in here, but you can see the stripes on his shirt here, and it all fades to just kind of one color. And again, we've lost some detail. There's one thing that's not really quite accurate about the way I simulated this. Does anybody see it? So in this original image, not everything is at the same distance from the camera. And that shape of that blob actually depends on whether something is in focus or out of focus. So I kind of implicitly assumed that everything was at the same focus when I did that. So that was kind of not a perfect simulation, right? And so now we can talk about what resolution is. If I look at this blob closely, I can look at the blobs and I can decide how close can they get before I can, if I two closely spaced point sources, how close can they get before the blobs are so close I can't tell them apart anymore. And obviously here, so here you can see the dashed lines are the individual curves. It's pretty hard to tell that it's impossible to tell there's two, right? Here, this is what Lord Rayleigh called just resolved, where the maximum of one lies at the first minimum of another. There are other resolution criteria. This one is just sort of the common one that's used, when to compare things. And of course, further apart than that, it's not too hard to tell them apart. So, so here's my airy disk, and then I'm going to do a little bit of math around Lord Rayleigh's criterion, which was again that the first maximum is on the first zero. And I've already told you I know this numerical. I know the angle of light that is accepted by my objective, and I get this equation for resolution: 0.61 lambda divided by the numerical aperture. Okay, so very important equation. Even though the answer is basically an arbitrary number, at least you can compare it among a lot of different objectives, right? Any questions on that? So, yeah.
Does it depend on the distance between
Yeah, so actually it does, but the numerical aperture number encapsulates all that, because the numerical aperture is the sine of this angle. So this is why long working distance objectives are expensive. If I want to keep the same numerical aperture and move the lens farther away, I need a bigger lens, right? And that's why the ELWD objective costs 5x the normal one. So okay, so now it's all set. Now I now know how much information does this thing gather, right? How many distinct points could I tell apart? And so that's why I vote for that as the most important number on the objective. Also, they don't print the field of view on there, which would be another very good number to have. The field of view of most of these objectives is right around 25 millimeters, except unless you buy just sort of the mainstream ones. Some of the other ones, it's different. But sort of the vanilla objectives are about an inch. And so in that numerical aperture equation, there's an n, right, which is the index of refraction of the medium. And so it's kind of puzzling. Why does that matter? And one way that you could think about that is, so if you have air there and you're trying to gather light from a specimen here, a lot of the rays are going to bend out and not be captured, okay? And if you were to increase the refractive index of the medium that's in between the lens and the sample, these guys are not going to bend away from you, and you're going to catch them. So that's why the n helps you. And in fact, the way I like to think about it is, say you could make this n infinity, right? Then all the rays would bend in, right? Would bend into the optic. And so you can increase the light gathering power of your objective by putting water or oil in between the sample and the first lens. And so what is it? So this is the bottom line is Na equals n sine theta. So if I buy the biggest lens I can with the smallest f I can, that makes sine theta close to 1. If I use the densest thing that I have commonly available as a medium, immersion oil is about 1.5. So the biggest Na I can ever hope for is 1.5. Okay, some people use more than one objective. It gets pretty difficult. There's exotic things you could do, but sort of mainstream. And I can use small light, right? So this gets down to 400 nanometers. And you guys, I don't know if you noticed on that curve of the dispersion of the lenses, that all the glass goes crazy as you start getting into the UV. So that's why you have to start spending a lot more money as you go to shorter wavelength light, right? And so this is kind of, around the shortest light you can, just sort of use in a vanilla microscope. And so you're stuck, 160 nanometers, that's it, right? That's kind of the best you could ever hope to do with just a regular light microscope. And that would be a big problem for biology in general, right? If that was the end of the story. Of course, there's all these really clever schemes for getting around that limit. Ooh, 320. All right, let's speed it up here. All right. So you can do various things. To get better resolution. So I talked a lot about why didn't people discover the structure of DNA with a light microscope. Well, probably all of you know how the structure of DNA was discovered. They used smaller light, right? So in that equation, smaller lambda means better resolution. And the only problem with small light is, like I said, the optics are crazy. You can't make optics for it. So what they do is they just basically say, forget the optics. I'm just going to look at it, and I'm going to get an image that looks like this, that looks nothing like the actual object. But this has a certain relationship to the object that I know. Does anybody know what the relationship of that thing is? It's the Fourier transform, right? So okay, so easy enough, right? Not a totally general purpose way to do things, but certainly effective. And then there's some other tricks that I can play, and I wish I had a lot of time to talk. All that different, the cells don't look all that different from the medium they're in, and this is a very problem. Even if you do make something visible, how do you know what it is, that you're looking at? And of course, so phase contrast, probably everybody has seen a phase contrast microscope, and that's one really good way, at least just for making things pop out from the background. And this is basically a technique that turns phase variations into intensity variations. Okay, and that's really useful because the change in phase is much greater than intensity, but your eyes are just not insensitive to it at all. Again, I think we don't have enough time. And then so again, all of these ways we're basically shining light through. And then, of course, probably the best thing to ever happen to contrast was fluorescence microscopy. Okay, and in this kind of microscopy, we're going to shine one color of light at our sample. It's going to emit a longer wavelength, and we're going to look at that instead. And so you can get all kinds of fluorescent probes, sort of broad categories. You can get these organic molecules. You can genetically encode the probes into the thing you're looking at, which we're going to be doing in the lab here. And there's probably no way to express how useful that is, right? It's incredibly useful. And then all of these things are a little bit dim, and they kind of bleach pretty fast. They kind of burn out. And then there's some things like quantum dots that are really bright and tough, and have some applications. So the basic thing is, and I know that you're going to have a big lecture on FRET and everything, and I'm sure they'll do this in much more detail. In fact, who wants me to do this Jablonski diagram? Nobody wants me to do it. All right, we're skipping it. Anybody? All right. So fluorescence, yay. Okay, and then good questions to ask. And then there's one other really important thing about fluorescence is it enables another whole set of techniques that get beyond this basic resolution. So this is a storm image. And in this technique, if you remember, the basic problem we had is that if there were two point sources close together, we couldn't tell them apart. And this is a technique where we basically turn the point sources on and off independently and look at them one at a time. And of course, I still can't resolve them. I can't see the point source. It's still a blob. But I can find the middle of the blob very accurately and tell where the point source was. And so we have a storm scope in the lab, and I think I have someone who agreed to maybe demo it for us, yeah? And so maybe during the rotations we'll be able to see that. So anyway, people get, incredible, sort of 10 nanometer range resolution out of this technique. And okay. So then there's kind of one more part to this whole story about you have to get the image out and analyze it somehow. And so you need some kind of detector to see it. And the most common, of course, if nobody uses film anymore, are these CCD cameras. And the way to think of these is this is basically it's a solar cell. It's the same thing. Light hits it, it makes electrons. And the electrons fall into a bucket underneath. And then you count them, okay? And you make these small, and you put them in an array like graph paper to make a CCD camera, all right? And so then you have all these buckets full of electrons, and you need to count them, there's a lot. This camera has about 250,000 buckets. A good camera probably might have 1 million, or more. And what you do is kind of this bucket. There's several different schemes for the way these get shifted out. But you basically kind of use a bucket brigade approach, okay? And you transfer all of the charges into a collector bucket, and then you measure them at the end, okay? And unfortunately, there are some sources of noise that arise during this whole process. And so these are the principal noise sources for a CCD camera. And so we'll talk a little bit about them. So there's shot noise, dark current noise, Johnson noise, and technical noise. And the amount of noise limits the amount of information you can extract from an image. So shot noise is a fundamental thing. There's really nothing you can do about it. And that is if you're counting a small number things that happen independently, that are statistically independent, you're not always going to get the same number. There's going to be variation in the number that you count when you're trying to estimate how many are there. So the way that the statistics of that add up is this is the Poisson distribution. And so for very small numbers, basically it ends up that the variance of this is the square root of the average number. So for very small numbers, the relative variation is very high. And mostly in fluorescence microscopy, you're looking at dim images. You're trying to divide them into a lot of little squares, and there just aren't that many counts and photon counts per square. And so there is certainly a realm where this shot noise is limiting. Okay, so that's a very fundamental thing you can't really do anything about, but it decreases with intensity. Of course, the shot noise, the magnitude of the shot noise increases as the intensity goes up, but the ratio of the noise, of the signal to the noise, gets better, right? And so we can these are uncorrelated noises. We can add them. They add in quadrature, and it ends up, as you reasonably would expect, that at low intensities, shot noise gets bigger, as you go up and dominates. But at low intensities, you're dominated by these other things, these dark current and Johnson noises that kind of set a floor of the lowest things you can see. And of course, all these things are, on a good camera, these will be specified. And the thing that you can do, let's see, I have a slide here. We'll go to that slide later. So, but basically, this dark current noise comes from the fact that the CCD is at some temperature and the electrons are have a distribution, and once in a while one of them will have enough energy to be counted, right? And so the way that you get around this dark current noise is you cool the detector down. And again, the real way you get around it is money, right? You pay a lot more money for a cooled camera. And then all the technical noise has a lot to do with good design of the camera, and also how fast you read it out. Generally, the faster you read it out, the worse the noise is. So when you're picking a camera for a microscope, it doesn't make sense to just buy the most number of pixels, because as you decrease the size of the pixels, there's less and less signal there, and you're going to get a worse signal-to-noise ratio, right? So it's kind of a balance. You would like to have a lot of pixels to see things, but it doesn't make sense to have a lot more pixels than sort of the optical resolution of your system. And just kind of as a rule of thumb, so if I plot here, this is the two sources at the Rayleigh distance apart, and kind of I want to have something in this ballpark. And believe me, there's a lot more papers and references on this, but basically, I would kind of want to have 1 pixel at the peak, 1 at this little dip, right? So that I could actually resolve that there were 2 things there. So that's kind of a rule of thumb of sort of about how big the pixels should be. And again, if you get a lot more than that, you're actually going to you're going to get noisy images. Yeah. All right. I wish I had more time to talk about noise. So these slides show the effect of cooling off your camera. And the EMC, the electron multiplying technology. All right, so this is what we're going to. So now this is stuff I have to get to, because this is what we're going to make in the lab. So, I'm going to start basically with this same microscope that we started with here, right? Except I'm going to add a mirror in it, and I'm adding the mirror because biologists don't like the goo to spill out of their samples while they're looking at them, okay? And so the mirror lets you put your objective facing up without having your microscope be this high, right? So this is my basic thing. So I have my objective, my tube lens, and again, only because Nikon told me if I use a 200 millimeter lens here, I will get 40x magnification. If I use a different number, I'll get a different magnification, right? And that's something we're going to actually have to play with in the design. So here's what I'm going to do. I'm going to add a component called a dichroic mirror. And this is a mirror that reflects some colors and doesn't reflect other colors. To first order approximation. It's actually pretty sloppy. It's like maybe a 90-10 kind of thing. And this is going to be a mirror that reflects green but not red, okay? So if I shine my green laser on this mirror and I align this guy so that this is shining up straight through my objective, I'm going to get green light falling on my sample. But there's a problem with this design as it is. Does anybody see it? It's not going to make me happy, yeah?
It's not white field.
Yeah, that's right. I'm shining a collimated light into the objective. So what's going to happen? It's all going to get focused down to a point, right? And so when I go to take, well, we know it's not a point, right? It's going to get focused down to an area disk, right? So when I go to take an image with this, it's going to look like that, right? And it's not going to make me happy. So how can I fix that? What can I do to fix that?
Lines by which
Yeah, that's right. I'm going to put a lens here, right? And that lens I'm going to arrange so that I'm focusing my laser at the back focus point of this objective. And now I have a nice collimated beam shooting out of there. Okay, so I'm happier, but it's still probably not going all right for me. So this laser beam is about a millimeter wide. So we buy very cheap lasers. Don't take any of the specs of the laser I give you with a grain of salt, but we say 1.1 millimeters. This camera is about 6 millimeters on the diagonal, okay? And so let's say I used a 200 millimeter lens here, and let's say I used a 200 millimeter lens here. How big is this laser beam going to be when it comes out? So if this guy expands light by 40x going this way, it shrinks it by 40 going that way, right? And so my imager is 6 times bigger than my beam, so probably my illumination is not going to be very uniform. Now, this laser doesn't really have a sharp edge. It kind of has a Gaussian-ish profile, and so it's going to be really bright in the middle and dim on the edges. So in order to fix that problem, I can put in a beam expander, right, which we already did as an example. I have it shown with a negative lens here. As I mentioned, don't worry, we'll be with you in the lab, but we're changing the beam expander design for what you guys are doing, and I might not have time to tell you about it now, but we'll tell you about it in the lab. And so what that's going to do is that's going to make my Gaussian wider, and it's going to make my illumination more uniform over the sample. And this is a trade-off, though, because the bigger I make it, the dimmer it is too, right? And the more power I need to pump in. Well, we're going to give you 5 milliwatts, about 1.1 millimeters, and so you can make this trade-off however you like. And so some people like to, some people like it really uniform, and some people like it more peaked. But wait, you can correct for it mathematically after for the non-uniform illumination, right? We can load that into MATLAB, and we can actually take a picture of what the illumination looks like and just divide by that, right? So we can correct that to a degree. Again, if the signal here is 1% of the signal there, your correction is not going to look too good, right? So okay, so logistics. So here's what we're going to do, and we're going to go to the lab. We'll show you where stuff is. If you haven't, like mounted and handled lenses before, clean lenses, all that, I don't know. Every time I teach the instrumentation class, somebody asks me what's a washer. We'll show you what a washer is. Any questions you want to answer? But basically, we'll do that for like an hour today. Tomorrow, you'll start working in groups of 4. I apologize, I don't like to work in groups that large, but I think it's the only thing we're going to be able to do. You guys will work it out. And so basically, you're going to choose, we'll show you kind of the range of components we have in the lab. You're going to choose components that will meet the design requirements. We're going to be building 2 different flavors of the microscopes. Half of you will be building blue-green. Half will be building green-red scopes. And then we'll go over the requirements with you. And hopefully tomorrow you'll get the transilluminated part of the scope working. Wednesday, hopefully you'll make fluorescence images, and then we're going to characterize it. We're going to measure, I didn't talk about this yet, but we'll measure the point spread function. That's basically we'll measure the dot. We'll measure the blob that a point source makes. All right? Any questions on this? Just show up. We'll get you through it. And then, so you might want to go over the block before you start building. Probably you want to go over your block diagram. Make sure that you're going to be meeting the requirements of the samples that we want to look at. All right. I spent a lot of my life putting stuff away. Please help me out, okay? Okay. So this is, all right. The lab very easily ends up looking like this, and we would like it to look like that. This is, let's see. All right. So because we're going to do the optics bootcamp right after this, I'm not even going to talk at all about this stuff, okay? But we'll teach you how to store lenses, mount lenses, how not to break stuff. We break a lot of stuff. Fortunately, we mostly buy cheap stuff. If you break something, just let us know. Don't worry about it too much, but try at least a little not to break stuff. And we'll go over this in boot camp. Okay, so now we have done enough stuff that we have our basic image acquisition model. So for the three of you who wanted me to talk more about transforms, look at the bottom half while I'm talking about the top half. And so basically we have an object that has an intensity defined as a function of x, y. We end up convolving that with some kind of spreading function. We add noise, and we end up with, that's what we actually get. And the shape of the blob that we convolve that with is really important. So this is an advertisement from a company that makes replacement lenses, intraocular lenses. After cataract surgery, they stick one of these in your eye. And you can certainly judge which one of these lenses you'd want in your eye, right? So this is my second example. So does everybody remember when they put the Hubble Space Telescope together and it was wrong? Okay, this is the point spread function of the original Hubble Space Telescope, okay? And I talked about this idea of like doing the undo button on the blurring. Well, so they did amazing things with the deconvolution of this thing as far as the images they got, but they still spent, I don't know how, tens or hundreds of millions of dollars going up to fix the thing, because if you start, more signal is better than more signal processing, always, right? And so they got much better images after. And this is you can think of resolution, this is something that comes up very often, is this thing called unwanted convolution, when your signal becomes entangled with some kind of function that you didn't want it to be. And so I showed you this slide already, and just to get some appreciation for the limits of this thing, why don't you just convolve with 1 over the thing? Yeah, that should work, right? And I have a demo of that. If you ask me, I'll show it to you. But it ends up that this has really small numbers in it. And when you invert them, they become really big numbers, and they multiply noise. And the thing, you cannot even recognize the image. If you just do this naive approach to deconvolution, you can't even tell what was originally imaged. Yeah, and so you have to be a little clever. There's a bunch of schemes for doing this, and anybody should feel free to ask me about. And even one more thing is, I mentioned how I didn't account for the depth in that image. Of course, you can view that the image space is a 3D convolution, so I'm going to stick my detector, somewhere in here, and depending on how deep my point source is, I'm actually going to get a different blob, okay? And just to give you some feeling for that, let's see. So this is oh, now I broke it. So these are synthetically generated bars. Oh, yeah. So this is going down. This is on the left is an image stack, going down through the bars. On the right is a 3D model being rotated. Okay, everybody gets that, I'm sure. And so this is to give you an idea of what the 3D convolution of that looks like. Okay, so if I look at my point spread function is in the upper right. Oh boy, everything's running slow. Okay, so that's the set of image stacks for my point spread function on the upper right. The upper left was my original bars, and then the bottom one. Boy, this is not running well today. Okay, so the bottom one is actually what it looks like when you do the 3D convolution of those things. So that's to give you a sense of what the point spread function looks like now. And on this slide, what I'm doing is I'm looking at that function side on, and I'm seeing what spherical aberration does. So basically, the limit of my optical system is the sum of this kind of diffraction problem plus the aberrations that I have in the system. And you can totally characterize that by measuring what the blob of light from a small point source looks like. And there's lots of reasons to measure it. When you do deconvolution, you can get a better result if you know what your point spread function looks like. And we have so one of the things that you'll do to characterize your fluorescence microscope in the lab is we have some slides with some very tiny fluorescent beads on them. You can image them, and you can use that to, at least you can image them in focus and estimate your resolution. If you're interested in doing the 3D measurement, I can set you up with that, but you're going to have to spend a decent number of extra hours in the lab. And if you do that, you can basically make a stack like this. And if you don't want to do it, I can show you some ones that we've measured on our scopes from other people. All right, so this is one last thing I got to talk about before we go. So this is on the upper right is a page from Isaac Newton's notebook. And in case you can't read his script, it's here in a modern font on the left. And so I'll just read it because it's one of the most shocking things I've ever read. And so he writes, I took a bodkin and put it betwixt my eye and ye bone, as near to ye end of backside of my eye as I could. And pressing my eye with ye end of it, there appeared several white, dark colored circles, which circles were plainest when I continued to rub my eye with ye point of ye bodkin. So the first time I read this, I had no idea what a bodkin was. And so fortunately, the Thimble Society has preserved 17th century English bodkins. And I call that a needle, actually. It's a pretty evil implement. So basically, he was trying to figure out what it is that stimulates your eye to see something. Again, along this line of what is light. And this brings us to our discussion of laser safety. It's a little known fact that he spent the next 2 years doing EHS paperwork after the bodkin incident. Okay, so I have a laser pointer here. This is this quote, safe laser pointer, right? You can't hurt yourself with it. Well, here's the criterion for, actually, this is a different story. I added this slide to my presentation a year or two ago because it was a front page story the same day I was giving a laser safety lecture. This is, you can order these really powerful, like 100 or 200 milliwatt lasers online now. And this kid decided to do a light show in his bathroom with one of them, unprotected, and ended up basically blinding himself. So we're not using any of those. All the lasers we're going to use are 5 milliwatts. And basically, eyes are incredibly interesting. They have an incredible range of tissues. I always am interested that in the cornea, the front surface of the cornea, you can scratch and it heals almost instantly. One of the fastest healing tissues in the body. And you scratch the backside, you're done for. It basically never heals, right? And so it's every little layer of it is totally optimized for what it does. And so if you look at eyeballs optically, you got to think about one thing. The lenses in your eye are underwater, at least the one that's in the middle of your eye. And what that does is that changes the value of the relative refractive indices, and it makes it be longer than it would have if it was in air. So your eye actually has a hard problem, right? It has to trying to get a lot of refraction in a small space, but it's underwater, and that's a very difficult problem. So actually, most of the refraction is in your cornea because that's out in air. So here's a bunch of the sort of relevant optical parameters of an eyeball. And so now we have done all the work we need to do to figure the optical gain of an eye. This diagram should disturb you. Always hurts me a little when I see it. So, okay, so this is this laser pointer, 5 milliwatts, okay? And I've condensed the two lenses in the eye into a single lens, a single equivalent lens. I have a 3 millimeter pupil, okay? And so I can figure out now basically the diffraction limited spot size that this laser will be focused down to when it goes in your eye. And if you figure it out, it's crazy, right? You get about 7,800 watts per square centimeter. That should say retina. And really, it's not that much because your eyes are actually your eyes are optically amazing, but because of the aberrations and different things in your eye, it's probably not going to be quite that much gain. But you can still easily get to 100 watts per square centimeter by shining one of these quote safe laser pointers at your eye. I mean I wouldn't want to like stick my eyeball in the filament of a 100-watt bulb or anything like that. But so the reason they call this safe is because it's bright. When it shines in your eye, you don't like it, so you look away or block the laser. You do something, right? And they basically say this can strike your retina for a quarter second and not cause any damage. That's the definition of a safe laser. And so is that really safe? So this was a case, also find very shocking. So this was a 11-year-old girl. She's on a school bus. And if any of your parents, this is horrifying. I'm not, so I'm not horrified. Well, I'm still horrified. All right, so she, on a dare, she stared into a keychain laser pointer, maybe 1 milliwatt, 2 milliwatts, less than 5. And she did it for maybe 10 seconds, nobody counted, and she did it on a dare. And basically, she developed a 2-degree blind spot in the middle of her affected eye. And so we didn't go over all the eye anatomy stuff, but basically all of the details of your vision are in that central 2 degrees. The rest of it, I mean, it's useful if you're getting chased by a lion and stuff like that, but all of the, everything you care about is in that middle spot. And so this was an extremely serious injury, and they estimated that she achieved 160 watts per square centimeter and a 6 to 10 degree temperature rise on the cells. And all of you that have grown cells know that 6 to 10 degrees is not very good for cells, right? And so if you get hit by a laser, the different tissues in your eye absorb differently. Some wavelengths affect the cornea a lot. Other ones, obviously visible wavelengths, make it through quite a bit to the retina. And UV can damage your lens. And so these are the lasers that we have in the lab. So we're going to be using these guys. I'll do a demo of the optical trap during the rotations. We'll have all the safety stuff for that set up. But it's hard to hurt yourself with these lasers, but it's not like if you could do it in theory. So we like to do things safe. By the way, you'll be using a version of it that's a plug-in if you're doing the green. The blue one is still, this is our, we like cheap. This is our blue laser, so it's a pointer that's we mounted. And so these are some really good rules, but the main thing is if you are using a full laser with collection optics, you should be wearing goggles. So here's some examples of goggles. And just out of curiosity, if you were doing a green laser, which one of these would you wear? I would wear the orange one. I like that answer. So just for comparison, orange one good, green one bad, right? So they all have markings on them, and you'll probably see me do this. Even though I know all of the goggles in our lab and wear them all the time, I still check them when I put them on. So all the wavelengths, and then there's this number optical density is printed there. So just make sure that the numbers are appropriate for whatever you're working with. But here's the best thing to do when you're working with your microscope is when you're making adjustments or anything like that, where did our filter go, Stephen? We have these neutral density filters. Do you know where it went? So, oh, is it here? So you can screw on a filter that will reduce the power of the laser by a factor of 100. It's basically impossible to hurt yourself with that little power. And so when you're making adjustments, I don't know where it went, but basically it screws on to the lens tube. Just put that right in front of the laser, make all your adjustments. When you're ready to use the thing, you can take it off, right? When everything is aligned and closed up on the optical path. That's really the best thing you can do in this lab. It's a little bit, the worst part of this is we have that 90-degree mirror that reflects the laser up, and you're kind of likely to lean over it. And so don't do that. And if you have the neutral density filter in, still don't do it. But you'll care less. Also, if you're wearing reflective rings, anything like that, don't work with them. And reflective tools can be, you can accidentally bring them through the path of the beam. But they're, like I said, they're safe lasers, not impossible to hurt yourself. So this shows you the markings on the goggles, but the most important thing is they're a last line of defense. They're not an excuse to do something dumb, okay? And oh, one other little weird thing that happens with these scopes, these are not real laser mirrors. They only reflect about 90 or 95%. And so you'll see there's a little kind of attenuated beam that comes out. Again, you probably couldn't hear yourself with it, but there's no reason to let that run around the lab. Stick a piece of electrical tape on the back of the mirror. Just get rid of it. And let's see. Don't worry about that. Okay. Oh, here's the best safety rule in the lab. Everybody always stands on the chairs. It's really dangerous. We have these little standy-on-y things if you need, yeah? All right. We have waste disposal. I assume you were beaten to death about that in the last lecture. We have liquid waste disposal. Ask us about it. This is about flat field correction, just because I didn't know where else to put it. But basically, I took an image of myself, and see, I had more hair then. So, it's a joke. All right. You guys, all right. So basically, I simulated it as if it had been lit by a non-uniform light, and then basically I divided by that and restored my the original uniform contrast of the image. Yeah. Oh yeah, and then don't save files in JPEG, okay? Because it just screws up your images. And oh yeah,